David Deutsch just exposed something shocking about modern science. Most quantum theories aren't actually science at all. They're just miracles disguised as explanations.
Rival interpretations that deny quantum theory will just say there is a collapse of the wave function, that it instantaneously occurs faster than the speed of light. And there is no theory of why that happens, but it does happen.
When you ask how quantum entanglement works, most interpretations by popular scientists, they basically reduce to magic happens. That's not science. That's giving up on our understanding of reality. David Deutsch is a quantum physicist at Oxford, a pioneer in quantum computing, and one of the most important theoretical physicists alive. He argues that only many-worlds theory actually explains what's happening in quantum experiments instead of just accepting it as a mystery never to be explained. This conversation reveals why modern physics has abandoned its core mission.
David Deutsch, welcome to the Into the Impossible podcast. You're perhaps the most requested guest in history that I have not had a chance to have on, so thank you so much.
Thanks for having me.
Love your writing, I love your thinking, and we have a lot to talk about. We'll run out of time before we run out of topics. But the first thing I love to do on this podcast is to do what you're not supposed to do, which is to judge a book by its cover. And one of the most impactful books in my life, my thinking, was The Beginning of Infinity, is The Beginning of Infinity. It continues to mesmerize and continues to be more relevant. It's kind of odd. I used to tell my friends and so forth that I hope my books become irrelevant soon after they're written, but yours seem to get more relevant. So I thought you'd help us judge the book by its cover, that the title of the book, the subtitle of the book, and the cover illustration. We'll put it up on screen for those that are listening or watching. You can find it on the YouTube channel. But David, take us through the book's origin story of its title and subtitle.
So it's my second book. In both books, if you want the origin story, it's something like that. I think that the concept of seeking good explanations is a better way of understanding rationality and science and all those related things, better than trying to follow a particular set of rules or trying to, especially not trying to be guided by the evidence or something like that. So I wanted to stress the consequences of thinking in terms of explanation. And that was already the case in my first book, The Fabric of Reality. But then colleagues said to me after it came out that I didn't actually explain what explanation is in that book. I just explained its role in other things. So I thought, well, yeah, that's true. And I'll write a quick thing about explanation as well. And that turned into a book. So that's why the subtitle is Explanations. And I forget, it's something about explanations.
The subtitle is, it's hard to see.
The explanations that transform the world.
That's the explanations that
so
transform.
The main title is The Beginning of Infinity, which stresses that the growth of knowledge is not inherently limited. That is, that there will never be such a thing as having understood physics, let's say. And there won't ever even be such a thing as having almost understood physics, like physicists thought in about 1900, before a flurry of new concepts and new theories overwhelmed them. So I think we're always at the beginning of infinity, in the same sense that if you choose a number, an integer, then it's always infinitely closer to 1 than it is to infinity. So we're always at the beginning of infinity. And as Karl Popper said, though we may differ from each other in what little we know, in our infinite ignorance, we are all alike. And that's another message of the book.
Yeah, it's a hopeful book. I think of you as the world's most optimistic pessimist or pessimistic optimist. I can't decide which, but since we can't approach infinity, and since we're closer to 1 than infinity or 0 than infinity in any situation, doesn't that immediately eliminate all notions of singularities from physical reality? I mean, how do you go from infinite temperature to infinity minus 1 Kelvin? I mean, it doesn't make sense. So does that not eliminate the possibility of infinity in the physical world?
No, because mathematical infinity is a different thing from physical infinity. Zeno of Elea, back in ancient Greek times, wondered how it was possible to walk across the room, because to get across the room, you have to first get halfway there, and before that, you have to get a quarter of a way there. And now we know even more that those are only rational numbers, but actually we've got to get through all the real numbers as well. So we have to do an uncountable infinity, different things, before we can walk across the room. And so we can attain that infinity because physics, the laws of physics, tell us that that is a finite operation. So it's physics that tells us which infinity is impossible and which is possible. And the walking across the room infinity, Zeno already knew that. He knew it was possible, but he didn't understand how that can be. And we now know how that can be with Newton and Leibniz having invented calculus and so on. So we can make sense of the infinite and the infinitesimal. So in regard to singularities like black holes and so on, the jury's out, because at the moment we don't have a theory of the singularity. We don't of infinite curvature or whatever. We only know that the existing theory doesn't cover it. But there may or may not be a theory like Newton's calculus or whatever that makes sense of that infinity, or there may be a better understanding that tells us that it doesn't make sense.
So one of the most fascinating things about mathematics is its relevance to the physical sciences, as Wigner famously stated it in his Nobel lecture, which you quote from in the book. But the other influence, at least in my life, mathematics and physics, was my late great mentor, Jim Simons. We just had a tribute to him in Manhattan on Friday. And at the ceremony, there was a Fields medalist, Ermino, can't pronounce his last name, young Italian physicist, as all Fields medalists need to be, under 40 or so. And he was talking, obviously, I'm very interested in Jim Simons' work on Chern-Simons theory and invariance that have application to cosmology and the Simons Observatory. But he was saying, in some ways, Jim Simons' work on minimal surfaces, which was some of the most beautiful mathematics that he had ever seen. And it made me think of what Jim had said about Zeno, which is that when he was 4 or 5, he realized he came up with Zeno's paradox on his own and also figured out that there must be a solution. He didn't understand it, but he basically said he taught himself mathematical induction. And the reason I bring this up is because it's another form of infinity is thinking about induction, except in some very strange circumstances where induction fails. For example, in Jim Simons' theory of minimal surfaces, which is basically if you take a loop of wire, say, and you put a soap bubble in between it, or you have 2 loops of wire, 2 circular loops, and you have a soap film between them, what shape does the surface of minimal area take on? So these are called minimal surfaces. And he proved that there are solutions to them without so-called singularities, where they come to a cone, and that is an infinite point of infinite curvature. And so that he thought that there existed minimal surfaces without singularities from dimension 1 through infinity. And he thought, he showed dimension 2, 3, 4, 5, 6, 7, and he got to 8, and then it stopped. And he said it was one of the most puzzling things he could imagine. Like, why the number 8? What is magical about the number? How does the mathematics know, in some cases, to sum to infinity, or sum to a finite number, and some cases to not sum to it? So I ask you that. How is it possible that there can be things where mathematical induction, works so spectacularly well, and then in other cases it fails, and we can't approach infinity even in the mathematical variety? How is that possible?
As always, and as in physics as well, we need an explanatory theory. If you just say something is true of the number 1, of the number 2, 3, you don't know whether that will stop. And even if it never stops, you don't know whether there's such a thing as infinity at the end of all that. So in the case of the walking across the room, that not only can you walk across the room, because the half plus a quarter plus an eighth and so on adds up to 1, there is something after 1. And you need, if you want to mathematize it, you need some axioms, say something substantive about the infinite case as well as all the finite cases. This is how Cantor developed the theory of infinity. So you can have the transfinite ordinals up to infinity, but then you have to have an extra axiom of transfinite induction that will tell you that for a given mathematical object that you've constructed, the transfinite induction will work as well. And if it's only the finite ones do, then the theory is silent about what happens. If you have a switch, if instead of walking across the room, you have a switch that's on until you get to halfway, then off until you get to 3/4, then on again, and then you ask, is it on or off when you reach the end? Now, you will reach the end, but whether it's on or off at the end depends on an additional assumption that you must make about the switch, over and above the one that you've made saying it can be switched on and off an unlimited number of times. You need something extra. And this shows you that there must be a thing that defines the limit or whatever you have at the end of the infinite sequence.
So Cantor was very quotable and quite a fascinating individual, and speculated a lot on the relationship between the mathematical and even the philosophical and perhaps theological. There are many quotes from him, but one of my favorite quotes of his is that a false contradiction, once arrived at and widely accepted, is not easily dislodged. And the less it is understood, the more tenaciously it is held. And one of the most shocking things to me about your book, The Beginning of Infinity, was that you get into these concepts of popularized by probably our mutual friend Richard Dawkins, which is the concept of the meme. And I wonder, in physics right now, what would you say is a sort of false conclusion that is not being easily dislodged and perhaps is being tenaciously held? Is there, in your mind, a pernicious theory, a thought, a fact that's inconclusive, that's wrong, that's being impossibly dislodgeable, shall we say?
Well, I think there are a lot of false theories in prevailing physics, and that's a healthy thing. There really ought to be, at any time, a lot of false theories which will eventually get replaced, superseded, when people solve the problem that their falsehood creates. In physics, and perhaps this is what you were referring to, I think there's something has happened to physics which is more than just falsehood. Falsehood is harmless. In fact, it's a condition for progress. What has happened is bad philosophy. In the late 19th century, there was the philosophy of positivism, which said that we cannot understand anything via theories that are not confirmable. Later, this turned into logical positivism, which said that theories that aren't confirmable by observation are meaningless. And then people noticed that that would mean that logical positivism was itself meaningless, since it's a philosophical theory that can't be verified by experiment. So then Wittgenstein concluded, yeah, it's meaningless, and all philosophy is meaningless, including mine. And people took this seriously, and people take this seriously to this day. It's just nonsense. It was nonsense from the beginning. Einstein was led astray by positivism in his youth, and it was only by rejecting it that he managed to invent conceptually new theories of the world. Positivism, to him, perhaps psychologically, positivism taught him the importance of asking what the theory says about experiment, about observation, rather than just assuming that it was the same as in the previous theory. That's true and harmless and beneficial. But the idea that things which are not verifiable are meaningless, that would have torpedoed special relativity and general relativity. It would have killed it in the cradle. So later, and when it came to quantum theory, Einstein was firmly on the side of realism. He was on the side of, there is a real world, we can understand it, we can't necessarily perceive everything in it, but we can explain what we do see in terms of things that we do not see. That was the beginning. The trouble is, this philosophy, positivism, which later turned into postmodernism and even worse things. It basically is the origin of woke as well. So there isn't an objective truth. There's only narratives about the truth. Those have seeped into physics, and they are the reason, in my view, why the Everett interpretation, the so-called multiple universes interpretation of quantum theory, has not had a wide enough uptake among physicists. But that's slowly improving, too slowly improving.
I want to discuss that, and we'll get to that. I have many questions about many worlds, again, from a more kind of simple-minded experimentalist perspective than a theoretical one. But before we leave Cantor, I want to bring up one other quote, which will dovetail into my next question about the kind of importance or relevance of induction. So he talks about himself in this quote. He says that infinite sets can be understood and manipulated, truly handled by the human intellect, just as velocity and acceleration are handled by calculus. So one thing to appreciate up front is that however abstract infinite systems are, after Cantor, he's speaking about himself in the third person, they are most definitely not abstract in the non-real, unreal way that unicorns are. Now, I don't want to talk about unicorns, although my daughter would probably like it if I did. But I do want to talk about this notion of, acceleration and velocity that he's bringing up, because in physics, at most in the continuum, we deal with, maybe third derivatives. There's something called the jerk in the cosmological context. We can measure the third derivative of the scale factor with respect to conformal time and cosmological time, and get out a term that depends on honest to goodness variables like the matter density, the cosmological constant or dark energy density. These are all subsumed into what used to be called the search for two numbers, but now we can talk about three numbers. But why not four numbers, David? The question I'm sort of trying to ask is, why does it stop? Again, what puts the not the magic into the equation? What douses the equations with water and puts out the fire at term three? And or am I being too pessimistic? Should I expect in future generations to find fourth derivatives among my graduate student thesis topic?
Well, of course, we can't prophesy the future of physics. We can't know anything about theories that haven't been thought of yet. And one way in which a new theory... So, as you know, the second derivative is of prime importance in fundamental physics. The laws of motion are all second-order differential equations, and this is for deep reasons. And we could imagine that will be broken in future by some new theory. If I had to prophesy, I would guess that the entire, I don't want to say paradigm because that refers to a very bad philosophical theory, but the entire structure of physical explanation in terms of differential equations of motion will be superseded. And I proposed this possible route to superseding it, called constructor theory, which is a generalization of von Neumann's constructor theory, but with respect to which, in terms of which, one can rephrase all the explanations of existing physics, but also the constructor theory has new laws of its own which aren't differential equations. It allows one to conjecture further new laws which are not expressed as differential equations. And the kind of thing that one might expect along these lines is the principle of the universality of computation, which says universal computers can be built within the universe to arbitrary accuracy. So that, of course, depends on what the laws of physics are. But to put that another way, if you make that a principle, it implies something about what the differential laws of physics are and the initial conditions. By the way, we have terribly bad theories of the initial conditions.
Yes.
It's really a contrick to say that we have good theories, universal theories of physics. We have very good laws of motion, and people refer to inflation theory as a theory of the initial conditions, but it precisely isn't.
Right.
It itself requires initial conditions that it doesn't fix.
Before I get to the relationship between the many worlds or many universes theory that you suggest support for in the book and inflation theory, I do want to get to that. I want to just ask, is that the job of cosmology to come up with a theory of the initial conditions? In that, if I study biology, even evolution, I don't have to come up with the origin of life. That's not a prerequisite, in my class. If I were to teach classes on biology, I wouldn't start with the origin of life. I mean, that's also an unsolved problem. So to what degree is it incumbent upon cosmologists or physicists even to have a theory of the initial conditions rather than describe everything that happens after those conditions, were instantiated?
There's no law that one has to be a physicist or a cosmologist at all. But the point is that there is a problem here. There is a problem that if we explain something in terms of, let's say, inflation, the inflaton field, and so on, then if we're going to do that, we have to assume something. We have to assume, for example, its initial condition. By the way, we could assume its final condition as well, or we could consume its condition after 3 days if we wanted to. With our kind of laws of motion, the conditions that you impose don't have to be initial ones, but we have to assume something in addition to the laws of motion. And it's a legitimate thing to think about. It's a legitimate thing to ask, why is it that and not something else? And that's, after all, how we got to the laws of motion. We want to understand the world. We'll never understand it fully, but But I think, and I argue strongly in the book, there is no aspect of it that we cannot ever understand. So if there's a puzzle, like what were the initial conditions, which you have to write down in order to apply the inflation theory, if the theory doesn't cover what they are, then it's open season for physicists or cosmologists or quantum field theorists or whoever to propose initial conditions, or to propose an alternative to this whole scheme of laws of motion plus initial conditions, which would imply enough of those to explain what we want to explain about the universe, such as why it looks homogeneous, why it looks isotropic, why it's as big as it is, all those things we would like to explain, and I think it must be possible, not to accept bad explanations or non-explanations of them.
So what do you make of the kind of sociological opposition to those that oppose the multiverse consequence of inflation? And I'm thinking about this letter that was submitted to Scientific American about 8 years ago by 20, 30 authors or so, Andre Linde, Alan Guth, and Frank Wilczek, and many Nobel Prize winners. And it was almost kind of like one of these missives, back in the medieval times in the Catholic Church. And so you could almost see, Galileo and Duchess of Tuscany or whatever going at it. But why is it such a source of turmoil, of passion, of open hostility? And in other words, Paul Steinhardt, who's a friend of mine, has been on the show, calls the multiverse not only bad science, but he calls it, dangerous to society because it sort of eliminates the impact of the scientific method, which obviously you champion in many ways in this book. So what do you make of the sociological opposition, the almost heretical camp that people who oppose inflation because of its multiverse consequence that seems to be concomitant with all instantiations of the multiverse, of the inflationary theory from Guth and Linde on down? I've had Linde on, I haven't had Guth on. But what do you make of the hostility to people that oppose the multiverse?
So there are several things here. The impolite sociological origin of the hostility, the simple one, and you asked for, you said you were going to turn to sociological things now, is simply because thanks to the way that physics that physics teaching has progressed during the 20th century, starting from there were almost no physicists in the world in, let's say, 1880, up to now when there are thousands of physicists studying every detail of everything. During that time, physics education changed drastically. And one of the things that has happened to it is that it has valued uniformity. It's valued creating an output from universities of people who meet the standard. In other words, people who are standardized. So I've told this story many times, but I only once in my life met Feynman, and we had a long conversation. And one of the many things we discussed was the future of physics. And he said, I mentioned something about, well, the great physicists do this or that. And he said, there are going to be no more great physicists. I said, well, I was a bit shocked. And I said, he said that there will be no more great physicists. And I was shocked, and I said, why? And he said, because of physics education. And he said that what I've just said, he put it much more in a much better way than I'm putting it now. But basically, he said that physics education, to get through the sieve of physics education, to get to studying fundamental things, one has to think in the prescribed way about physics. Whereas in his day, it was almost the opposite. You got to the top by thinking in a different way. It's true that you had to be expert in certain ways. Being different from everyone else was that's what they were looking for. And I think that's very true, although I would not be so pessimistic as to say that there will be no more great physicists. I just think of this phenomenon as one of many, bad things happen in the world, and that's one of them, but they can be fixed. And the more one draws attention.
But isn't he expressing your belief that we're closer to the beginning than to the end? In other words, the low-hanging fruit has been picked. Is that not what he's saying?
No, because I don't think there is such a thing as low-hanging fruit. Because the whole process is potentially infinite, there is no such thing as encountering an obstacle because you're too close to the end, because all the low-hanging fruit is gone. And actually, in my actual view of what the situation is, I think there's more low-hanging fruit now than there was in 1900.
Wow.
Michelson gave his famous talk in, what was it, 1890 something?
1894, yeah.
1894, saying that future physics will all be about the sixth decimal place. And, after that, you had radioactivity, you had quantum theory, you had relativity and general relativity and thermodynamics. And he couldn't have been more wrong, except that it really did look almost complete. So he can't be faulted for thinking that, unless, he would have needed a better philosophy, not a better grasp of existing physics. Today, we're in a completely different position. We have these two superb theories, quantum theory and general relativity, and they can't be unified. That has not happened. That wasn't the case in 1900. Everything looked finished. Now it does, now it looks as though it's inconsistent. The whole edifice is inconsistent. But more than that, the individual theories, quantum theory is fine, looks fine if you didn't think about relativity, but quantum field theory looks terrible. It's just a set of rules for trying to get predictive answers at the expense of having an underlying explanation that doesn't make sense. So we don't have a theory of what quantum fields actually are. If you thought that they were fields that are quantum, you'd be wrong. They are a set of rules where you write down things with hats on them representing operators. But when they depend on X, they don't really depend on, when they depend on position, they can't really. And even in ordinary quantum mechanics, if you have the fundamental relation that the commutator of X and P is I, then take the trace of both sides. The trace of a commutator is 0. The trace of I is infinity times I. So 0 equals infinity times I. So so you're told that that's not what we really mean. They don't really mean that those are operators on a Hilbert space. It has to be rigged. It has to, and so on. So we do not have an explanatory theory underlying quantum theory, even though it works so well. We do have one for relativity, but we know that it can't be true because of singularities and because of its inconsistency with quantum theory.
Well, let me ask you about that, David, because into my, again, I'm a simple-minded experimentalist, but the only two places where we would seem to need a quantum theory of gravity is at the, singularities, near singularities of both black hole variety and perhaps in the origin of the universe. And many people believe that the origin of the universe can be quite easily handled without a singularity. So we may not even need it there. And I've asked this to your friend Roger Penrose, and he seemed to agree. But I wonder what you feel. I mean, there's no letter from God that says we need to have a quantum theory or a unified theory of anything. In fact, most physicists chase the theory of everything without even recognizing that we have no existing grand unified theory. So they're kind of, I always say they're skipping the gut and going straight to the toe. But in reality, I mean, who says we should expect there to be a quantum theory of gravity when it might only be of interest in the core of a black hole?
So there are several things there that I disagree with. One of them is this idea of what we need from physics, from theories of physics. You seem to be using need in the sense of need in order to make predictions.
Yes.
But I don't want to make predictions about the origin of the universe and what's inside black holes and so on. And most of the people in the world don't even know that those are problems. What I want to do is what every human wants to do, is understand the world, the aspects of the world that are interesting. And the aspects of the world that are interesting to physics are the properties of space, time, matter, and so on. So that's one thing I would say. I would say that this idea of need in terms of needing to predict is a mistake. More, it never works out that way. For example, my colleagues, Chiara Moletto and Vlatko Vedral, have suggested experiments that in principle could be done in the laboratory that depend on quantum gravity, depend on gravity being quantized. Now, these are really elaborations of an idea that goes right back to the 1957 Chapel Hill Conference, which began much of modern physics, where Mr. X, otherwise known as Feynman, contradicted other people who were then saying, do we really need a theory of quantum gravity since it'll never be measurable? And he produced a thought experiment where it's inconsistent to say that there is no theory of quantum gravity. Now, for that to be inconsistent logically is one thing, but it turns out, as it so often does in physics, that once you've got the possibility of something being different and being different at the explanatory level, some clever person is going to think of an experiment. And you can't say in advance that there can't be an experiment because you can't have an explanation that says you can't have an experiment.
Right.
There's only an explanation that says, in principle, you could have an experiment. So I think it's just not true that we don't need a theory of quantum gravity. And by the way, quantum gravity, as I said, is only one of the many things that's wrong with physics at the moment.
No, I agree. There's no shortage of crises in physics
right.
Yeah. But so let me pivot to the experimental, kind of verification. Again, that's always going to be the lens through which I perceive or attempt to comprehend things. From the perspective of many worlds hypothesis, which you have recently said, and you say in the book, and you say just a couple of maybe tens of minutes ago, that it hasn't received as much attention, et cetera. But there are a great many people who not only give it attention, I'm thinking of Sean Carroll and others, but basically assume it's correct and that it is the most economical and the most generative and the most predictive and the most consistent, at least with us, kind of a classical brain. We have these classical brains. Here's one that my kid made for me on a 3D printer. But at the same time, I have not heard of many predictions of the outcomes of experiments or even how we could go about designing an experiment. I asked Sean this very question. I said, if I think of the basics of the many worlds interpretation, which you know obviously much better than I do, David, but I said, I would like to know, well, rate does this branching of possibilities take place at? Is that is that at the Planck scale time? Is that at Planck time? Is it at something closer to a collider timescale, femtoseconds, or even clock timescales that friend Bill Phillips, who was a guest and won the Nobel Prize for atomic lattices and fountains and stuff, they're making quite precise clocks nowadays. So is that, how would you approach it? First of all, let me take one giant step back first, David. I'm sorry to ask an interweave question, but you're a theorist, and yet you obviously value experimentalists to a great extent. What is the minimum that you would want your theoretical graduate student to know about the experimental process and its limitations? And then, if you would, can you think of an experiment to put the many worlds theory to perhaps a falsifiable test, a decisive test, as Popper calls it?
Yes. So I would want a theorist, someone who wants to do research in theoretical physics, in fundamental physics. I would want them to understand the epistemology of Karl Popper. And one of the things and that's it. That's it. Everything else follows from that. One of the things that tells us is that there is no such thing as a test of a theory. There is only a test of comparing two theories, two or more theories. So one thing we would need before testing quantum theory, and as I often say, the calling the Everett interpretation an interpretation is already misleading.
Sure.
We try and call it Everettian quantum theory now to make it unambiguous, but really it's just quantum theory. It's the claim that quantum theory, as we have it, is a theory of the world, and that means it has to be an explanatory theory. So it has to say not just what the outcome of the experiments will be, but why, what process brings about the outcome given the initial conditions that we set up or given the preparation? What brings about the outcome? And the Everett interpretation is the only, Everettian quantum theory is the only explanatory theory in that sense. It has no rivals. Its only rivals are of the form, well, if you set up the quantum system this way and then a miracle occurs, then you will get this answer. There is no other thing other than Everettian quantum theory tells you what actually happens. Also, it solves various conceptual mysteries, like in an entanglement experiment. How does the information of what you have measured at one end get to the other end? And again, other interpretations other than actual quantum theory, let me say that correctly now, other rival interpretations that deny quantum theory will just say, well, there is a collapse of the wave function, that it instantaneously occurs faster than the speed of light. And there is no theory of why that happens, but it does happen. And that violates relativity. But more importantly, it rejects explanation on principle. So when you ask for a test of just Everettian quantum theory, I'd need another theory to test it against. And for example, there's Roger Penrose's theory, which one could, in principle, I mean, I think we're getting very close to being able to test it, which says that the equivalent of a wave function collapse happens when the difference between the mass of two states of the space-time exceeds the Planck mass, 10 to the minus 8 kilograms. And with quantum computers, we're very close to that. So that would be a test. But without Penrose's theory, or without some other theory like that, which is an alternative to quantum theory, there is no such thing as a test.
So in terms of the falsifiability criterion, which Popper is obviously most well known for, at least in this context, originally his bête noire was astrology and phrenology, I think, and dream interpretations, which were fashionable at the time. And I wonder if Popper were around right now, what would he say about the many worlds? I mean, what would he say about the multiverse from cosmological perspective? It doesn't, again, according to eminent theoretical physicists, Neil Turok, Paul Steinhardt, many others, that this is not good for not only science, but for society. And, in his words, astrology is not testable, but it is testable. I mean, I'm a Virgo and, my horoscope says I'm going to win the lottery tomorrow and I don't win it. Well, it's falsified. So how would a modern Popper, perhaps, would he revise the falsifiability criterion at least?
So it's a mistake to characterize Popper's epistemology as the falsifiability criterion.
Sure. I just said the most prominent, the pop psychology version of it.
Yeah. No, but here I'm going to be dropping another name for the one time I met Popper. So there was one time I met Feynman and one time I met Popper. And
wow.
It was in the company of Bryce DeWitt. And we tried to persuade him of the Everett interpretation, as we called it then.
Oh, wow.
And he was very strongly against it, but absolutely not on the grounds of untestability. He was worried about various things, like where does the mass come from when the universe splits in two? That was one of the things he wanted. What he would like to have explained. Now, at that time, so Bryce DeWitt had also for years been saying that the terminology of a universe is splitting is wrong, but we didn't have a proper explanatory alternative to that, but we do now. So now we have a picture of the multiverse where it doesn't split. What happens is that continuously, and this is, I think, answering the beginning of your question, how often does the split happen? A continuous differentiation. If you think of the universes in the multiverse as being like a continuum, like along the real line or something like that, then when it changes from having a majority of one kind of thing to a majority of the other kind of thing, that happens when the partition between the two changes, except that that would suggest that a particular universe gets swept up by the change as the change passes by. But that's not the case because the different universes are fungible. There's no such thing as which one. Just as when you have a particle that's tunneling through a quantum barrier, and you say, well, why does it tunnel through? Well, because the proportion of high momentum and low momentum things changes. You can work out what proportion of them have a given momentum and a given position at a given time, but you can't say of any one position what is the momentum of all the things with that position, of all the particles with that position. So they are they don't have a separate identity. And by the way, this happens in a more pedestrian way in waveguides. So you can have a waveguide with two photons in the same state, and then you can allow one of them to escape. But there is no such thing as which one. So, or to put it another way, you can have you can put one in when there's one, and then there's two, and then you can say, well, let's take out the one we put in. There's no such thing. It's meaningless. There is a difference between having one and having two, but there is no such thing as which one. And it's the same, it's exactly the same, and for the same reason about universes. Another thing, just to add complication to this story, since you asked, universes are an emergent property of the multiverse. There is no exact, it's like geological strata. There's no exact point on a geological stratum where you can say, at this atom is where the lower stratum ends and the higher stratum begins. They are. You can only see universes zoomed out. Once you zoom in, you find that they affect each other, and therefore they're not parallel. And therefore the thing as a whole can't be described as a set of universes. So that's another reason why there is no problem of instantaneously changing from one to another.
I wonder if that's, been revised again. That's the work of Jim Simons and this Fields medalist that I have to look up his name. But they've done work on this problem, first identified by Stefan, of Stefan Boltzmann fame back in 1895, the ice melting problem. Like, what is the boundary of the ice melting between the ice and warm water? This is what Stefan was interested in, Joseph Stefan. And, he couldn't solve it back then, but I guess with minimal surfaces and other approaches, which are, by the way, completely irrelevant. Fractal geometry has nothing to do with fractals, apparently, has well-defined dimensionality. But I wonder if that mathematics or anything has relevance nowadays, because it seems to be, closer to a solved problem, this boundary. And I wonder if that's true of geological strata and therefore per force to the multiverse. What would you think about that? If we could say that.
I don't know that theory, but from what you say just now, it sounds to me very plausible that the mathematics could be applied to that as well. It could be applied to all those cases. It's like from the beginning of physics thousands of years ago. There's this tension between the discrete and the continuous. We want, ultimately, we don't want to have the divisibility of the world stop, but on the other hand, we don't want to have it infinitely divisible either, because then that leads to paradoxes. But to a large extent, this, as I said before, this was solved by mathematics, things like calculus, and I think that the equivalent problem in quantum theory will be solved when we have a better theory of the structure of the multiverse. I always say we don't have the equivalent of in relativity. We have a theory of differentiable manifolds, which tell you what the field equations of relativity, what they refer to, what the object is in reality that these equations are referring to. The what you could think of the metric or the curvature or something as just mathematical objects which you manipulate to find out things like the perihelion of Mercury advancing. But we know more than that. We know why it happens. This is always my concentration on explanation. We know why the perihelion of Mercury advances because we know what space-time is doing to make it advance. We have no such thing in quantum theory. We have only the equivalent of the field equations and the metric and the curvature. We know that there is a thing that this refers to, but we don't know what that thing is. We don't need that thing to make predictions, but we do need it to understand the theory. And by the way, another reason why we need to understand the theory is that it's almost always essential in discovering the next theory.
So I mentioned you to Nima Akani Hamed last week at this symposium I was at, and he has this theory of the amplituhedron, or it's basically trying to construct Feynman diagrams without space and time, because he echoes Lorentz, who said that, space-time is doomed, et cetera, and only some weird amalgam will persist. But I pointed out to him, which he didn't appreciate at first, but I think he agrees now, with the interpretation that you make in the book, which is that his theory, I don't know if you're familiar with it, but he basically has all these different vertices. All that matters is ordinal numbering, or, the numbering of particle states. Let's say you have an electron in and scatters off another electron, and you don't care what happens inside, but there's only a finite number of permutations, which, could be, as you point out in the book, could be Roman numerals, it could be tally marks of sheep or whatever, but it's space-time agnostic. It doesn't depend on space and time at all. It's just the number of permutations that could arise, and then given the number of cancellations, this is motivating him because he agrees with you that quantum field theory is sort of very incomplete, much less complete than relativity. And yet he still maintains that relativity is not the final word either, because we don't have a quantum theory, which again takes me to this teleological point. What is the purpose of what you theorists are doing versus what we can do as experimentalists? And I promised my audience I'd ask you about, the implications of inflation. And you already mentioned earlier today, it seems like a little bit of, I wouldn't say skepticism about inflation, but a dissatisfaction perhaps with it as an incomplete and almost I quote you something to the effect of the opposite of the initial conditions. Can you explain that? Because I would have thought before this call began that you would support inflation because of its allied concomitant prediction of the multiverse, which, if proven correct in some sense by our experiment or my competitor's experiment, hopefully, we'll get there first, but who knows? But the point is, David, why are you, sort of a little bit more critical than I would have expected, or am I wrong, of inflation?
Well, I don't operate by guilt by association or innocence by association. It could be that either of the theories could be false, or one and not the other, or I doubt that either of them can be true.
Yeah,
But,
right.
I think they'll both be superseded. I was only saying about inflation theory. I think the argument that there is an inflation field and that it is responsible for some of the features of the early universe and so on, I think that's pretty much unanswerable now. Maybe somebody will come up with an even better theory, but at the moment, that's the best we have. I was just pointing out that not just inflation theory, but all quantum theories at the moment lack a good theory of the initial conditions, and that's not especially a criticism of inflation theory. When I say we have no theory, we have some theories. We for example, we had the theory that the cosmological principle that the universe is homogeneous and isotropic, perhaps. Okay, then people pointed out that under the laws of motion, given that there's a Big Bang at which everything started, the inhomogeneity today must be traceable back to an inhomogeneity at time zero. It's impossible that a completely homogeneous universe can evolve into an inhomogeneous one. So there was a problem. So it was thought that maybe the theory of inflation would solve this, because you could say, let's start out with an inhomogeneous universe, and then go through this inflation process, which will reduce the inhomogeneities by a factor of 10 to the 60. And we're not going to argue about factors of 10 to the minus 60, are we? Well, unfortunately, yes, we are, because to say that the inhomogeneity at the beginning has to be much smaller than now doesn't solve the problem that we thought there was a principle of homogeneity. That principle must be false. What replaces it? And it's no good saying we'll never know experimentally. First of all, as I said before, the chances are we will, because some clever person will invent an experiment to test rival theories of this. But also because I think that the human species, and physicists in particular, want to know what the world is actually like, what the world actually is, not just what we can predict it will do to us. That's secondary. We want to know what is there. Just like people who believe in God want to know that God is there or not there, because that's how they understand reality. And when they change from one religion to another, they're changing something substantive, even if there is no experiment that can distinguish between the two. You can criticize theories on grounds other than their experimental implications. You can criticize them on the grounds that they are internally inconsistent, that they don't explain what they purport to explain. There are many grounds on which one can criticize philosophical theories. And when it comes to theories of physics, even more, as I said, because in practice, it will come down to an experiment eventually, even if we can't think of one initially.
So constructor theory, in some sense, again, my simple-minded interpretation, please forgive any errors, that reality is sort of predicated on what transformations are possible and which are impossible. But you mentioned the word God, and I wasn't planning to go there, and we can skip it if you don't want to talk about religion or God, but I find it fascinating in many contexts. And so is God the ultimate, constructor? Is that a way of solace to the needy, or am I reading too much into it? Is there a place for God in constructor theory?
No, because constructor theory isn't about that. So it's not. So constructor theory, it's only a shorthand to say that constructor theory is about what's possible and what's impossible. That's just a reformulation of the existing way of looking at physics. Constructor theory is about, so possible and impossible are technical terms that we use as shorthand to mean the existence of a constructor to cause that transformation is or isn't possible. And the constructor is something that brings about the transformation without being changed itself. So an example of a constructor is like a heat engine or a catalyst. It does things to other systems without being affected itself in its.
But isn't that the unmoved mover? Couldn't God play the ultimate catalyst?
One could have a theory in which God was the ultimate catalyst, yes. But one can have many theories within the realm of constructor theory. And there are, I think, independent reasons, nothing to do with constructor theory or even with physics, to reject theories that rely on the supernatural. So the trouble with the supernatural is that it always involves something inexplicable. That is, there is no theory of how it works. There's no theory of what brings about its behavior. So with a catalyst or a heat engine, we can have detailed theories about why this particular chemical is a catalyst and what it does when the chemicals that it acts on lodge themselves in a groove in the catalyst and so on. We can have an explanatory theory causes its catalysis. And it's the same with heat engines. Study of such things has in the past, long before constructor theory in any form, even von Neumann's, such things have led to understanding physics much better. So when Count Rumford noticed the cannon, when he bored the cannons, they got hot, and then he worked out how much heat was produced by how much boring them, then we got to understand heat, work, and thermodynamics through considering what this doing things to cannons why doing things to cannons did what they did, and what was possible and impossible to do. For example, is it possible to bore the thing in a certain time without it getting hot, and that kind of thing. So with the supernatural, we can't do that, because the whole point of the supernatural is that we can't do that. If we could, it would be natural. we would have a theory of the dynamics of God or whatever.
So staying on constructor theory, but now applying it to my field of specialization in cosmology, if we get away from the question of the initial conditions, could constructor theory be viewed as a possible cataloging scheme for which cosmic transformations are possible or are impossible? Could we reframe perturbation theory in the cosmological sense of constructing, what types of values for the fundamental problems of the fine-tuning of constants that seem to be apparent, or the arrow of time? Is that a possible, something that we could look forward to in cosmology application of constructor?
It's certainly something we can look forward to. In fact, again, my colleague Chiara Marletto and her colleague Maria Violaris investigated constructor theoretic thermodynamics and got some very nice results. Again, the experimental implications are thin at the moment. But for example, surely you will like the fact that in constructor theoretic thermodynamics, the first law of thermodynamics is information-based. It can be defined in terms of information, just like the second. So that tells us that the first two laws of thermodynamics are both statements about information, but only via the constructor theoretic formulation thermodynamics. We haven't even applied constructor theory to general relativity yet, let alone to cosmology. So I can't even give you hints of that form for the future of constructor theory. What I can say is that constructor theory seems to be perfectly suited for answering questions that are puzzling in the existing formulations. For example, what is the expression of the equivalence principle in quantum theory? So in the equivalence principle says that, if you're in a falling elevator or accelerating elevator, you can't tell whether it's a gravitational field or not. There he is saying that. But the thing is, that only works for arbitrarily small elevators. As soon as the elevator has a non-zero size, you can tell whether you're in a gravitational field or not.
That's right.
The gravitational field has a different effect.
Tidal forces.
On tidal forces. So in quantum theory, there is no such thing as an arbitrarily small elevator, because if you make the elevator too small, the energy of the photons goes up. And so one way or another, you can't get into the situation that the equivalence principle pontificates about. But it looks as though, and we're not there yet, but it looks as though a constructor theoretic version of the equivalence principle will express both the general relativistic one and be extendable to quantum theory as well.
Staying with quantum mechanics, I am, if you'll indulge me a few more minutes, David. I know it's later there than it is here, obviously, but I do want to get back to the elevator question, but in the context of artificial intelligence. But before we do that, I want to talk about the context or the extent to which dark matter and dark energy, which are pervasive, literally and figuratively in cosmology, are they what you would consider an explanation? And are they good explanations, or are they merely just token placeholders for which we have no experimental instantiations of? Are they good explanations?
That they are there is a good, though very sparse, explanation. That is, they can't be varied and still account for what we see. There is no explanation of what they are, and that is something that's missing at the moment. They may not even fit into the existing scheme of fundamental physics. That is, they may not be quantum. By the way, there's also the inflaton field.
Yes.
So there's I don't know why people always say that there's those who really, there are three fields that we don't know about, and they might not be the same kind of fields that we talk about in quantum field theory. So that maybe something new is needed, but certainly we don't have not only not good explanations, we don't have any explanations of what they actually are.
So yeah, that's quite condemning. I would have said that the inflation field would be even below the other two or three, if not for the Higgs field, that we discovered a scalar field, existed at least in one instantiation as a Higgs boson. But that, only marginally gives some credence, unless it happens to be linked in some way to dark energy or the inflaton field. But I did promise we're going to talk about the Einstein equivalence principle, because actually, I'm sorry, let me, my editor cut that out. Before we go to the Einstein equivalence principle and Einstein's elevator, David, I wonder if we could talk about the recent developments just in the last 6 months. I've had on the leaders of the Vera Rubin Observatory, the leaders of the DESI experiment, which seems to indicate that dark energy at 1 part in 32,000, being a fluke, or 4.2 sigma exclusion of the cosmological constant. Has that discovery, if it's confirmed, which it seems to be, quite a strong tension, if that's confirmed, David, would that revise any of the arguments you make in the beginning of infinity? Would it make, say, the omega point or something more plausible, which you mentioned, but you sort of say, you seem to lean on the best evidence of the time, which when it was written was just when the Nobel Prize was awarded to past guest Adam Rees and Brian Schmidt on the podcast in 2011. So have you revised any of the conclusions in the cosmological sense only, keeping in mind my audience is full of Nobel Prize winners and cosmologists? What would you say now, or would you write anything different about the conclusions on the basis of cosmology in the beginning of infinity based on recent data?
So I think that cosmology has done an unusual thing between, let's say, 1995 and today. In those 30 years, the amount we know about cosmology has gone down. I suppose it's a bit like what Michelson, what was known about physics and dynamics and so on. And in 1895, the subject seemed to be almost complete, and 20 years later, it looks as though it was completely not understood at all from the ground up. And then only in 1926 did it start being understood again. I suppose 1915 as well. I'm not sure I would write anything different. I mean, I would certainly not endorse the omega point theory as true or as the best available theory. I would certainly say that it's on the cards that it is true, despite what was thought in between then and now. It might well be true, but we'd need a good explanation. We don't have, since we don't have a theory of dark energy, for example, we don't know whether the dark energy could be harnessed by people in the future to produce free energy. If it could, then computation can go on forever. Life can go on forever. If we can. If we can't, then according to the best cosmological theories today, life and so on will come to an end in 10 to the 100 or whatever it is years after the fabric of space-time has been ripped apart by the dark energy. This is all. There's nothing explanatory there. This is just speculation without substance. We can speculate anything, like the dark energy might stop working tomorrow. Who could we sue if that happened?
The National Health Service would be
right. Yes.
They're always a safe bet. But I want to push back with love and respect on the statement that you made that our knowledge has gone down. I mean, since I was a grad student in 1995, we've discovered the flatness of the universe from the CMB. We've discovered black holes colliding at cosmological distances. When I was a grad student, we thought the universe was open and matter dominated. We had, theories, basically very preliminary notions of what the context of gravitation would look like on cosmological scales. Certainly, we didn't have the knowledge of the neutrino oscillations on cosmological disks. Anyway, there's a lot that you said there by saying it has gone down. Can you clarify what you meant by that?
So
at least experimentally, it hasn't gone down.
These discoveries have contradicted what was thought before. So in that sense, knowledge has gone up. As a result of knowledge going up, the problems with the theory, with the general theory of cosmology, have increased, not decreased. You keep saying I'm down on these theories. I think that's a good thing. I mean, this is how I want science, especially fundamental science, to look. So we didn't know. Well, we suspected there was dark matter, but we didn't really have good evidence or a good theory of how it works. We didn't know anything about dark energy. That was a complete surprise. So we now have more problems with having what's the cosmological version of a worldview? Our cosmological worldview is now seems less secure than it seemed in 1995, and that's a good thing. That is, I think we should always enjoy being puzzled and perplexed, because that's what causes progress.
And I am optimistic about it. And I do agree with you that it is a good thing. I didn't mean to imply that you're down on it, just that the notion that things have gone down when surprise or information has gone up seemed a little bit puzzling to me. But I think that dovetails nicely into a discussion on artificial intelligence, which you also, it's remarkable how much you predicted. I mean, for a guy who talks negatively about prophesizing, you seem to do a lot of prophesizing that's correct, David. So maybe that's an ironic gift that you have. I want to ask you about some basic thoughts I've had on artificial intelligence. The first one I want to talk about is one you alluded to, which is 1907 paper by Einstein of the Einstein equivalence principle. So if you're listening, I've got my favorite puppet out here, Albert Einstein, and he's going to fall. And he realized that if the elevator cable broke, he would experience no gravitational field. He could zero it out effectively. And that had great power for constructing the later field equations. It took him a long time to get the field equation, but he eventually got to them. But I want to ask you first, David, in that paper, he calls it the happiest thought of his life. It's really a note, not a paper. And I want to ask you, is it even possible in principle to conceive of a machine that A, has a happy thought? What does that even mean? And B, could visualize the visceral sensation of free fall in an elevator or going over a roller coaster hump? Is that not something unique to the human embodiment of natural intelligence, therefore making it impossible for artificial intelligence to construct interesting new theories of physics, for example, like the Einstein equivalence principle?
We are such machines. So obviously it's possible for them to exist.
But in computing, in silicon, in qubits form, and any form you like, an artificial intelligence to replicate that.
Well, so an intermediate step before considering AGI would be, is it possible to build a human being from scratch out of atoms? And I think that that is clearly not forbidden by any fundamental theory that we have. Obviously, we're nowhere near being able to do it. You just showed me a 3D printed brain. What we need in principle is simply a much higher resolution version of that, and presumably a scanner as well, unless we want to make a new kind, but I'm not sure that we know how to do that. That's a separate issue. But to copy a person is, I think, fairly obviously not ruled out by any existing fundamental physics. And then what is really operating to make the subjective sensation of falling and that kind of thing is not different between neurons and whatever your toy brain is made out of. If you could make the toy brain out of materials that did something analogous to the information processing in brains, then it would, it would say that it experienced that as well. But I think that it's obvious that it would experience it, because when we say that we do experience it, we're actually consulting our memory of experiencing it. We never experience what's actually happening in a particular instance. We only ever experience what has happened to us 1/5 of a second or more ago. And what's more, we are interpreting it. And all that is computations. And we know no machine can perform computations that are different from the ones that can be performed by a universal Turing machine, or if you like, the universal quantum computer. Although I very much doubt that the quantum computations are necessary for human cognition.
So the notion of embodiment, I talked to Noam Chomsky about this many years ago, but he seemed to think it was critical to have an embodied, and again, that's not impossible. So therefore it must at some point be explored and a proper question. But in the near term, do you think it's more likely we could get a Turing test that's based on a new law of physics, not or some new discovery, or even an old law of physics that's finally understood and more predictive and more explanatory, but only on the basis that it's embodied in some sense? In other words, what part of what you do as a theoretical physicist is only made possible, enabled by your physical embodiment?
Well, my physical embodiment in my brain. So the way I look at it is that I am a computer program. In other words, I'm an abstraction. I am not the brain. The brain is just the hardware on which I am running, but I am software. So I am therefore embodied in the brain. If I were embodied in something else with the same computing power, then I would be embodied in that. And if it didn't have the rest of the body, like the arms and legs and so on, then that would be equivalent to being in a sensory deprivation tank. But a person in a sensory deprivation tank is still exactly as much of a person as when they're outside. And, if you lose a limb, you don't say, I'm less of a person now. Or, you might say that, but you'd be saying that metaphorically. You're not less entitled to the vote or less entitled to human rights if you lose an arm. And I think the same is true of the brain. That is, what counts in the brain is the running program. That's what is conscious. That's what has feelings, and that's what is embodied. When you talk about something being embodied, I am embodied in the brain, mostly. It's also, the rest of the body also plays some role with chemicals and so on, but that's, again, all just information processing. And the brain is the most important because it's the only one in which error correction occurs.
I want to ask a hardware-related question. You mentioned software, but I can't resist as an experimentalist mentioning hardware. And that's this phenomenon known as lock-in. One of my favorite examples is the Hubble Deep Field could have been a lot deeper, and we could have learned a lot of the things that took until the James Webb Telescope at much greater distance from the Earth at the L2 Lagrange point, 1 million miles from Earth, as opposed to 630 miles above the Earth. And that was set by the width of a horse's rear end. And I don't know if you know this story, David. Have you ever heard this? Okay. So this is at least partially true. But the space shuttle was launched using solid rocket boosters. Those solid rocket boosters were made in Utah in the western United States. And the space shuttle was launched from Cape Canaveral in Florida. So they had to traverse from Utah to Florida, which is 2,000 kilometers plus, something like that. And on their way, they had to go through at least, 7 different tunnels in train tunnels. And those train tunnels are a certain width. They're set by the width of the gauge of the railroad. And 2 of those tracks side by side is what determines the maximum width of something that can go through such a tunnel. Well, now we go back another step and, what sets the width of the railroad gauge? Well, that was set by the width of horses that used to pull a standard gauge chariot going back to the Roman Empire. So two horses were used to pull chariots, and that's the actual width. It's something like 2.3 meters or something like that. And that's the width of a railroad track, which is now half the width of the tunnel that the booster had to go through. And the altitude the booster gets to is proportional to its area, its specific impulse. Its jerk, if you will, is determining what altitude it got to. And that caused us the Hubble Space Telescope, launched by the space shuttle, to get to an altitude of about 400 to 600 kilometers or something like that. And that meant it went through the atmosphere and experienced something called the South Atlantic anomaly. And it also had day-night cycles every 90 minutes, which is bad for the thermal regulation of the camera. At any rate, David, the point I'm getting to is that no one would have thought that the Hubble Deep Field image of a galaxy would not have been as good because of the width of a horse's butt was too small. If it had only been bigger, we would have had high, But I want to turn that type of thinking into a question about AI, because we talk a lot about AI. Again, you predicted immensely presciently in this book from 14 years ago. Many of the things we're just now seeing, and anticipated some things we haven't yet seen, but I'm wondering if we'll ever will see them because of lock-in. In other words, the LLMs that you and I use every day are based on GPUs married to LLMs. And those GPUs were designed such that my kids could play Minecraft a little bit faster than their neighbor and kill him, before he kills my kid in the game. They weren't designed for this. They happen to be exceptionally well suited to matrix multiplication, inversion, and other things, right? So I'm wondering, did that lock us in to a finite ceiling on what computers can ultimately do because of the trillions of dollars that are going into GPU plus LLM, and not into alternative modes of artificial intelligence that could be actually useful for physics and determining new laws of physics, etc. What do you think about that argument?
I think that sort of thing is bound to be ubiquitous, and it's bound to slow things down compared with not having that thing. But it cannot impose a bound. So it can make things happen later than they otherwise would, but it can't stop things happening. For example, with your horse's rockets, if that horse's butt thing were really the impediment to space travel, then by now, it would have prevented the Hubble Space Telescope from being better, and you could imagine a scenario where it prevented all sorts of other things. But by now, if there was a factory in one part of the US and you needed to get the rocket to the other part, then Elon Musk would make a reusable rocket into which you could put that rocket and would transfer it that way. Would simply take off in one place and land in another. And then the problem would be solved, except probably it would be expensive. But then the problem of expenses also solved in the long run by creativity.
If today's conversation with David Deutsch made you question everything about modern science, you need to watch my recent episode with Sabine Hassenfelder. We got into how mathematical beauty can guide scientists astray and what the true power of quantum computing and artificial intelligence may turn out to be. Click here, and don't forget to like, comment, and subscribe.